Welcome to today's lesson on surface integrals. The rest of Unit 16 is going to cover surface integrals. What is a surface integral? How do we calculate it? What does it represent? And then similar to line integrals, we're going to learn some theorems or some ways that will make it easier to calculate some surface integrals. So before we even talk about a surface integral, let's talk about what integrals we've done so far. We've done a single integral, a double integral, a triple integral. We've done a line integral. And remember, the line integrals can look different. The C represents the line integral, and sometimes you have ds. Sometimes you have dr. Sometimes you have the line integral with that little circle, which tells us that we have a simple closed region, and so we can use Green's theorem. But remember, with Green's theorem, of course, your orientation or the orientation of your surface has to be positive or counterclockwise. So what we're going to do now is we're going to integrate over a smooth parametric surface. So what we did before is in 3 space, we had something here that we integrated over, some type of curve. And this generally represented what we call a lamina. And what we're going to be doing now, instead, we're going to be integrating over a thin curved plate. And that is going to get us into surface integrals. So let's say that we have some vector field R, so we can see it's a vector, in terms of variables u and v. And x, y, and z are all functions in terms of u and v. Okay, so we have some space in the UV plane that's going to give us our region D, and we're going to take that region and we're going to split it up into rectangles, and then we have our little rectangle here. And what's going to happen is that R, so this R, is going to take our section here in the UV plane, and it's going to put it into the x, y, and z plane. So we're going to form a Riemann sum. And this is our Riemann sum. This delta S is the area of one of the patches. So we're taking the function value at some point, and we're multiplying by the area of the patch, like we've done before. So if we take the limit then as mn approaches infinity of, again, the function value times the area of the patch, what that becomes is a surface integral of f of x, y, z ds. So the above expression represents the surface integral of f over our surface S. So the way that you know it's a surface integral is it's going to have an S down here instead, and it's going to be a capital S here to represent our surface. And so, of course, the logical questions are, how do we actually calculate this surface integral, and what does it actually represent? What is the meaning? So that's what we're going to talk about, and then we will look at some examples. Okay, so to evaluate, you have 2 options. If you have parameterized the surface, then what you're going to do is you'll have the double integral over the region D of f of r of uv multiplied by the magnitude of ru crossed with rv dA. Now, we skipped this lesson, so this probably doesn't jump out to you, but that has a meaning. That is actually the surface area of our surface S. So this is how you would evaluate the surface integral if you had parameterized. Now instead, if your surface is rectangular, the way to evaluate that surface integral is this is going to become the double integral over the region D of f of x, y, and z then we're going to write as a function of x and y. And we're going to multiply that by the partial of z with respect to x squared, add the partial of z with respect to y squared, add 1, dA. And again, that should look familiar with surface area also. Of course, we're going to do examples with both parameterizations and rectangular coordinates. Before we do that, though, let's talk about interpretations. You can calculate the mass of an object if we have the surface integral of just ds with no function, or our function being 1, that would give us surface area. And it will also help us calculate the center of mass. So in our class, we didn't do center of mass, but you could. The way you would calculate mass is the surface integral of rho of xyz ds. Rho is just density. It's a density function. And then if you wanted the center of mass, I'm going to give you x bar, which is the center for x. Of course, you would have to do y and z. That would be 1 over the mass, and then the surface integral of x multiplied by rho of xyz ds. Similar idea for y bar and z bar. So like I said, in our class, we haven't focused on center of mass. It's just another application. Okay, so let's see this in action. Example 1, evaluate the surface integral of x squared ds over the sphere x squared add y squared add z squared equals 1. So first thing to point out, how do we know it's a surface integral? We have s with a double integral. So a line integral would be c and a single integral, and then we have a capital S instead of a lowercase. So what we're going to do is we are going to evaluate using the first option. We're going to start by parameterizing this surface. And we're going to do that using spherical-like coordinates. And the reason I say that is in this case, rho is 1, right? Our distance from the origin is just 1. So x is going to be sine of phi cosine of theta. Y will be sine of phi sine of theta. And z will be cosine of phi. So r then is a function of phi and theta. Okay, so looking back, with the parameterization, one thing that we're going to need is we're going to need the cross product of RU and RV, and then we're going to need the magnitude of that. And then we'll deal with that F later. So this is the big thing that we're going to have to calculate. So in our case, we're taking R of phi and crossing it with R of theta. So I'm going to write out my partials first just to make sure I give myself enough space. So I'm going to take the partial of each of these above, first with respect to phi. So when I do that, I get cosine of phi, cosine of theta. And then I get a cosine of phi, sine of theta. And then I get negative sine of phi. Now I'm going to find R of theta, so I'm going to take the derivative with respect to theta of our parametric equations. So I get negative sine of phi, sine of theta, sine of phi, cosine of theta, and 0. And then up here we have ijk. Okay, so this one is going to be a bit of a doozy. Remember, ignore first row, first column. We're going to cross, subtract cross, and keep going. Okay, so when we do that, for the first component, we're going to get sine squared phi cosine theta. For the second component, we're going to get sine squared phi sine of theta. And the last component, we're going to get sine phi cosine squared theta, add sine phi cosine sine squared theta. Okay, so looking if we can simplify this at all. The first two components, of course, we can't. For the last component, if we factor out sine of phi cosine of phi, we're going to have cosine squared plus sine squared, which is just 1. So that becomes sine of phi cosine of phi. Okay, so then from here, of course, what we need is the magnitude of R of phi crossed with R of theta. So if we do that, we're going to get sine to the fourth of phi cosine squared theta, add sine to the fourth of phi sine squared theta, add sine squared phi cosine squared phi. Okay, so again, here we have cosine squared add sine squared. So that gives us just sine to the fourth of phi And then we have sine squared of phi, cosine squared of phi. So hopefully we can see if we factor out a sine squared of phi, we're going to end up with sine squared cosine squared again. So this is really just the square root of sine squared of phi, which is just sine of phi. Okay, so all of this was just the background work to evaluate this surface integral. So if we remember, it's out of view now, but we had the surface integral of x squared ds. So what we're going to do then is this is going to turn into a double integral. X squared, well, our expression for x was sine of phi cosine of theta squared. And then we have that sine of phi from above. And we're going to integrate with respect to phi and then theta. Phi, if you remember, the bounds are 0 to pi. Theta, the bounds are 0 to 2 pi. Okay, so what I can do, because I have rectangular coordinates and because this is a function of phi multiplied by a function of theta, is I can split them up just for ease of evaluating. So this becomes 0 to 2 pi of cosine squared of theta d theta multiplied by 0 to pi of sine cubed of phi d phi. And that's what we're going to have to evaluate. Hopefully you left yourself more room than I did, because I'm going to have a very hard time fitting this in. Okay, this first one, we've seen this in a few different examples. The substitution for cosine squared is 1/2 add 1/2 cosine of 2 theta. So integrating then, this will give us 1/2 of theta add 1/4 sine of 2 theta from 0 to 2 pi, which gives us just plain old pi. And then this sine cubed, what I'm going to do is I'm going to turn it into sine of phi multiplied by sine squared. But sine squared I can turn into 1 minus cosine squared. Okay, the reason I would do this then is if I multiply it out, I get sine of phi, subtract sine of phi, cosine squared theta, or cosine squared phi rather, d phi, and then I can integrate that. So this becomes negative cosine of phi, add 1/3 cosine cubed of phi, evaluated from 0 to pi. So when I substitute in theta, I'm going to get 1 subtract 1/3. When I substitute in 0, I'm going to get negative 1 add 1/3, which is 4/3. And then if we remember all the way back, these were being multiplied. So my pi multiplied by 4/3 gives me a final answer of 4/3 pi. So as you can see, when you parameterize the curve, it's quite a good deal of work. Now we're going to see the next example in a minute where we can easily use the rectangular coordinates we're given and we don't have to parameterize. Example number 2, evaluate the surface integral of y squared add 2yz ds, where s is in the first octant of the plane 2x add y add 2z equals 6. So we saw from earlier that we can take a surface integral f of xyz ds and change it into a double integral over the region D of f of x, y, g of x, y, and so on and so forth. The reason that I'm showing you this is we need to take our z and write it as a function of x and y. That's going to be part of the first step. So what we're going to do is we're going to use this s to solve for z, which we then can substitute in to our function. So we get z is equal to 1/2 times 6 subtract 2x subtract y. And then if you remember, after this f of xy, g of xy, we're also going to need the expression for surface area. So we're going to need the partial of z, which with respect to x, which in this case is -1, the partial of z with respect to y, which is -1/2. And then from before, you're going to take that z of x squared, add it to that z of y squared, and add it to 1, which ends up being 3/2. So from here, what we can do then, our surface integral of y squared add 2yz ds is going to become a double integral, rather, of y squared add 2y. Our z is going to be replaced with that 1/2 6 subtract 2x subtract y multiplied by 3/2 dA over the region D. So if I simplify all of this, I can pull out that 3/2, and then I end up with y squared subtract 6y, add 6y rather, subtract 2xy, subtract y squared. And now let's figure out what that region D is. To figure out region D, we're going to have to sketch in or have some idea of what this visual of S looks like. So we have a z-intercept of 3. We have an x-intercept of 3. And we have a y-intercept of 6. So this is a portion of the plane. So this is our region S. Region D, since this is a double integral, is just going to be in the xy plane. So this is our region D here. So if we go to find the equation of this line, it's y equals 6 minus 2x. So I'm going to integrate with respect to y first and then x. Y goes from 0 to 6 minus 2x, and x goes from 0 to 3. And now we would just evaluate this like a typical double integral. We've done many of these before, so I'm not going to go through the evaluation part. I'm just going to tell you that you get an answer of 243 over 2. So at this point, you've seen two surface integral examples, one where we chose to parameterize the surface and one where we didn't. You're going to have to decide whether you can stick in rectangular coordinates easily, like we could here, or whether it might be easier to parameterize. Now, when we did line integrals, after learning how to calculate a basic line integral, we looked specifically at vector fields. And so that's what we're going to do now. Now, to remind you, if we do a line integral of a vector field, the main application of that is work. So now, if we do the surface integral, again of a vector field, that calculates what we call flux. Before we talk about what flux actually is, we're going to have to go through some vocabulary and some conditions before we get to the definition of flux. In this case, we're not really thinking of a vector field, we're thinking of what we call a flow field. For a flow field, we're thinking of F as representing the velocity of a fluid particle at a certain point. And so, like I said, before we get to what is flux and how do we calculate it, we need to talk about oriented surfaces. So some surfaces are what we call orientable and some are not. A surface that is orientable has two sides. We often call them the outside and the inside. What is important for you to know is this is what we're dealing with in this class. And so then your next logical question would be, well, what is a surface that's non-orientable? A surface that's non-orientable, for example, would be a Mobius strip. And what you're going to notice, if you can see here, I know the visual isn't great, is if you're walking around the outside of this, like picture you're an ant, eventually you're going to be going to what would be considered the inside of the figure. So this is a non-orientable surface. It only has one side. You start on the outside, eventually you're going to get to the inside. So some things to know. N is a unit normal vector at each point. The opposite of n is the unit normal vector in the opposing direction. Unit normals are never going to have an abrupt change in direction for an orientable surface. So you can see here, you're not all of a sudden going to be going from straight up to straight down if you have an orientable surface. So if it's an orientable surface, you're not all of a sudden going to have an abrupt change in direction. It is not possible all of a sudden for n to be going down here. So that is not possible. Okay, so what we are often interested in when we have an orientable surface is the positive or natural orientation. So So the orientation of a parametric surface is defined by n. So this n, this unit normal vector, is called the orientation. The way that you find that is you have a parametric representation in terms of u and v. You cross the two partials, and then you divide by the magnitude to make it a unit vector. So that's going to give you a unit vector with what we call the positive or natural orientation. And we're going to need that natural orientation as we move on. So let's take a look at an example, and then we'll start talking more about flux. So here's our example. Find the natural orientation for r of uv equals cosine of u, comma v, comma negative sine of u. Okay, so first thing I want to talk about is, what does this look like? Maybe you already know, maybe you recognize this. Cosine of u, sine of u is going to be a circle moving along the y-axis. So we have something like this, and it's going until y equals 3. So this is our surface, it's a cylinder. So we want to know what the natural or the positive orientation is for this cylinder. So to find the orientation, I'm going to have to find the partial with respect to u, cross it with the partial with respect to v. So I have I, j, k. My partial with respect to u is negative sine of u, 0, negative cosine of u. Partial with respect to v is 0, 1, 0. And that ends up being cosine of u, comma 0, comma negative sine of u. Now to make this a unit vector, I'm going to have to divide by the magnitude. The magnitude is just 1. So that means n, our unit normal vector, is cosine of u, comma 0, comma negative sine of u. Okay, so what does that mean in terms of natural orientation? Well, let's consider the point where u is 0 and v is 0. That gives us the point 1, 0, 0. And it also gives us the unit normal vector 1, 0, 0. Okay, so 1, 0, 0 is right here. And if we point the vector towards 1, 0, 0, it's going to go this way. So what that is showing us is that outward is the positive orientation, positive or natural. So the negative orientation is going to go in the opposing direction, which is inward. So if we took the vector and pointed it in the opposing direction, that would be the negative orientation. Okay, so this orientation is going to be important now for calculating flux. So now we can finally talk about what is flux and how do we calculate it. So there are two basic conditions. The first one is we are only going to deal with incompressible fluids. So we're only going to deal with fluids that have uniform density. And we are going to assume that the velocity of a fluid at a fixed point does not vary with time. And that is called the steady state. Okay, so the definition of flux then is the volume of a fluid that passes through a surface in 1 unit of time. And that, of course, is going to depend on many factors, which you can probably come up with. The first one, of course, is the speed of the fluid. And that should make sense, right? Greater speed is going to be a greater volume. So the faster that the fluid is moving, the more that is passing through the surface. Secondly, how the surface is positioned. Relative to the flow. So this is going to be a little difficult to see two-dimensionally on a video, but I'm going to do the best that I can. Let's say that this is your surface. And let's say that the flow is parallel to the surface. Then there's no flux. and that's because nothing passes through. Right? If the fluid is moving parallel to the surface, nothing can pass through. Now, on the other hand, let's say you have a different surface, and this time the fluid is perpendicular to the surface. If the fluid is perpendicular to the surface, this is when we have maximum flux. And that is the fluid is perpendicular to surface. So then lastly, the flux or the volume of the fluid also depends on the area of the surface. And that should make sense. If we have a larger area, flux will be higher, right? Larger volume moving through the surface. So now that we know what flux is and what affects flux, let's take a look at how to calculate it. So if you remember, just as a quick note, with work, it was that line integral of f dot dr, and that's how we saw it was work. That dr is what indicated to us that it was work. What's going to indicate to us that something is flux is this ds as a vector. So with surface integrals, normally it's just d big S, but as soon as you see s as a vector, that tells you that we're calculating flux. Okay, so how to calculate flux then? This is the same as the surface integral of f dot the orientation ds. Okay, so then the way that we can write that is this becomes the double integral over the region D of f. This orientation we found to be r of u cross r of v divided by the magnitude and then this S, surface area, is the magnitude of R crossed with the magnitude of V dA. So finally, what we're able to do when we simplify all of that, we find that flux is the same as the double integral of F dotted with the vector that results from crossing RU and RV. So that's how we're going to calculate flux. As you can see, unlike earlier when we did surface integrals, we are going to need a parametric representation. So either we're going to hope that we get a parametric representation, or we're going to have to come up with one. So let's see an example where we calculate some flux. Example 4, find the flux of the vector field F across the unit sphere, x squared add y squared add z squared equals 1. So we don't have a parametric representation for this surface, so we're going to need one. Now, we already saw this previously in the video. We're going to write in terms of phi and theta. So we get sine of phi, cosine of theta, sine of phi, sine of theta, cosine of phi. And then from previously, we're going to know that we need to take the partial with respect to phi, partial with respect to theta, and cross. So this was cosine of phi, cosine of theta, cosine of phi, cosine of sine of theta, negative sine of phi. And now if I take the derivative with respect to theta, I'm going to get negative sine of phi, sine of theta, sine of phi, cosine of theta, and 0. And hopefully you remember we already did this earlier in the video. This ended up being sine squared phi, cosine of theta, sine squared phi, sine of theta, and sine of phi, cosine of phi. Okay, so now we're finding flux. So our flux, remember not double integral, surface integral of f dot ds. And we just saw that we can write this as a double integral over the region D of f dotted with the cross product of RU and RV dA. So next thing I'm going to do is I'm going to find that cross product. So I have to have f in terms of theta and phi. And I'm going to dot that again with r of phi crossed with r of theta. So this I'm going to write in terms of our representations here for x, y, and z. So when I do that, I get cosine of phi, sine of phi, sine of theta. And then our last one is k, which is sine of phi, cosine of theta. And I'm dotting that with this cross product from above. Whew. So let's see where that gets us. That will get us cosine phi, sine squared phi, cosine of theta, add sine cubed phi, sine squared theta, add sine squared phi, cosine theta. And unfortunately, that cannot be simplified. So now finally, we are ready to go to our flux. This is going to be a double integral of that dot product from above. And then convention is to integrate with respect to phi and then theta. Remember, we talked about the bounds for phi 0 to pi, bounds for theta 0 to 2 pi. Okay, while this looks really bad to integrate, it's actually not that bad. First thing I want to point out is that these two terms are the same. So if I could add them together and pull a 2 out, and then I can actually separate phi and theta. So I'm going to take out sine squared phi, cosine phi, d phi, from 0 to pi. And then I have that 0 to 2 pi of cosine of theta. Similar idea for this term. I can separate phi and theta. So this gives me 0 to pi sine cubed of phi d phi multiplied by 0 to 2 pi of sine squared of theta d theta. And then here's what I wanted to show you. What is super nice, if you recognize this right off the bat, the integral from 0 to 2 pi of cosine of theta is just 0. That's just 0. The area, if we think about the curve of cosine, is the same above and below the x-axis. So that just gives us 0. So really, what this becomes is the integral from 0 to pi of sine cubed of phi d phi multiplied by 0 to 2 pi of sine squared of theta d theta, which ends up as 4 pi over 3. And if you don't remember how to do that integration, it's very similar to example 1 from these notes. You just need a few trig substitutions. So look back at example 1 if you want to remember how to integrate sine cubed or sine squared. Okay, so the next logical question that's going to come up, and this is the last thing we're going to talk about, is what happens if you have a non-parametric surface. So what happens if you have a surface that it is not easy to write that surface parametrically? How are you going to calculate the flux? Well, let's suppose that we have some function z that is a function of x and y, and let's assume that it is a surface oriented upward. Now I want to emphasize here, upward orientation is not the same as positive or natural. So upward does not mean positive or natural. Okay. So what we're going to do then is we're going to rewrite that function as z subtract g of xy is equal to 0. Now the reason that we're going to do that is we can then calculate n, the natural orientation. We're going to write that as the vector negative partial of x, negative partial with respect to y, comma 1, over the magnitude well then, if we call all of this g of x, y, z, the way that we can rewrite n then is that is the gradient of g over the magnitude of the gradient. So where that leads us is if our figure is oriented upwards, then we get the surface integral of f dotted with negative z of x, negative z of y, 1, dA. If the surface is oriented downwards, on the other hand, we get the surface integral of f dotted with z of x, z of y, negative 1, dA. So we'll see an example in a minute, but I want to tell you how I remember this. Upwards, I think of like positive, so the last number has to be positive. First two are negative. Downwards, I think of like negative, so the last number is negative, which means the first two are positive. That's the way that I remember. Okay, I know you guys have stuck with me for a long time. We're going to look at one more example. Evaluate the surface integral of f dot ds, where f is the vector field y, x, z, and S is the boundary of the solid region E enclosed by z equals 1 minus x squared minus y squared and z equals 0. Assume outward orientation, and that's the convention. First step before we actually jump into any calculations is to look at a figure so that we know what's going on. As a reminder that ds, where s is a vector, tells us that we're calculating flux. Okay, so let's look at a figure then. Z equals 1 minus x squared minus y squared is a hemisphere with a radius of 1. And then z equals 0, of course, tells us that it's just the top half. And so in this case, we actually have two surfaces. We have this first surface, which is the unit hemisphere, and we're assuming outward orientation, which would be like this. And then we have this circle here also, assuming outward orientation. So we're going to actually need two pieces for the flux. We're going to need to consider surface 1 and surface 2 separately. And if we look, surface 2 has a downwards orientation, which tells us that when we do our vector, the third number will be negative, which means we have positive z of x, positive z of y. And then our blue surface, our first surface, is upwards. So that last quantity will be positive 1, which means we have a negative z of x and a negative z of y. Okay, so now that we know those partial vectors that we're going to have to take at some point, let's first consider our initial surface. So our flux, surface integral over S1 of f dot ds. So this is going to become a double integral over the region D. We're going to have to write this f in terms of our surface. So that becomes y, x, 1 minus x squared minus y squared. And then we are dotting that, like we said, with this vector here. Partial with respect to x, but the opposite sign, which is 2x. Partial with respect to y, but the opposite sign, which is 2y, and then positive 1, dA. So then this becomes double integral over the region D of 2xy, add 2xy, add 1, subtract x squared, subtract y squared, dA, which simplifies to double integral over the region D of 1, add 4xy, subtract x squared, subtract y squared, dA. And try to find bounds here for x and y, which would just be that circle on the xy plane. Hopefully we can see that polar, converting to polar is going to make our life a whole lot easier. So if we convert this to polar, it's going to be 1, add 4 r squared cosine theta sine theta subtract x squared and y squared is just r squared. And then if you remember, when you convert to polar, you get an extra r, dr d theta. Our r is going from 0 to 1, and theta is going from 0 to 2 pi. Now, I'm not going to spend time to integrate this. I will tell you, though, if you do integrate it, you get pi over 2. Okay, so next thing that we're looking at is that surface 2. That surface 2 is on the xy plane. So that is actually the equation, just plain old z equals 0. Because it's just that bottom plane z equals 0. We're no longer using this hemisphere from above. So now we have our surface 2 of f dot ds. And this is going to become double integral over the region D. We again have to rewrite f in terms of this new surface z. So that's going to be y comma x comma 0. And then we're dotting with, like we said, this red vector. Z of x is 0, z of y is 0, so then we get -1 dA. So this becomes then double integral over the region D of 0 dA, which of course is just 0. To get our final answer, we would add our two quantities together, and so we get our flux to be pi over 2. Again, and if I asked you what does that mean, that is the quantity of fluid that is passing through our surface in a given unit of time. Okay, I know this video was long, and I really appreciate you guys sticking with me. Just so you know what's coming up, we've got 2 more videos left in this unit where we are going to be looking at other ways to calculate surface integrals or other theorems. So I look forward to seeing you next time.